Hey guys, thanks for tuning in. If you like this video, please give it a thumbs up and subscribe to my channel. That will be much appreciated. This is just a demonstration of how a power system consisting of 5 busbar system can be drawn or represented. So this is for students doing a design project requiring them to draw and study the layout of a particular power system network consisting of 5 busbars. So these have been drawn already. This is a circuit, a network that have been taken out of a giant network map. So I'm just going to quickly show here what actually is going on here. So we can have here location 1. So we have a symbol that show here. This is a symbol of a power station. So it could be a nuclear power plant, or it could be what do you have? A thermal power plant, anything, or a wind turbine power plant, or hydroelectric. So now this power plant here is supplying 100 MVA, that mega volt ampere. So basically there's a SC here, that's meaning short circuit. So basically that's a magnitude of a short circuit MVA you can get if you have to get a fault here. Now the system at the first bus bar here is supplying 132 kilovolt. So that's the highest potential in this bus bar. So we name this as location 1 from the grid. Now we got switches here. So basically isolators. So this one here, this can be a representation of a substation. So we are getting power from the grid and it going into a switching system from the substations. And from there we have the output that's also going now out via our circuit breakers and isolators. Now you have a distance that is traveling. So the distance here we say from location 1 to this location 2. This location 2, which is busbar 2 of the system. So this is busbar 1 and this is busbar 2. Now from here to here we got a total distance of 4.5 kilometer using a cable system. Now the cable name here is Busbar, which is rated at about 650 amps. Now you can locate this cable and other specification from a table that's got all the references, because basically since this is a cable, this is a network, so you will have an impedance that is embedded in the cable. So using that table of reference, you can replace this reference here with an impedance, and that will help you to determine what will be the short circuit current at this point, because now the current have traveled from here up to here. So there is a small drop here because of the impedance of the line. So that's what you can do. Now you move to busbar 2, which is location 2. You still have 132 kilovolt also from the grid. Now because we haven't got any transformer on the substation, this is just a switching substation, there is no transformer stepping to a different level. Now from there you will have basically the same system, but it's a different bus bar which is basically moved to a different location. So for instance, we move from a power station, we went over the mountain or over a small bush or something to a new substation that is now going to switch to a different location. Now from this substation here, as we can see, there are 2 transformers here, T1 and T2, with 2 circuit breakers. Now these, you can see these transformers are stepping down from the 132 to 11 kilovolt. Now this could be a remote location, a small town. So the small town will have a small a substation constructed to extract power from the 132 to a low level substation to get to 11 kilovolt for distribution. So that is Busbar 2. Now we're moving on to go to Busbar 3, which shows here location 3. Now from Busbar 2 to Busbar 3, we also have a line. We got a cable system, also 4.7 kilometer of length, also 650 amps of rated capacity. So basically it's the same cable we are using from Busbar 1 to 2, also using from Busbar 2 to Busbar 3. Now, so you'll use the same references you use there to implement it here to replace this cable with an impedance value. Remember, it's an impedance, not a resistance. So there will be a resistive element or there will be an inductive element into the cable. Together, that will give you an impedance with the power factor, whether it's a lagging or leading power factor. But you go decide what you get there. But I'll give you a hint. It's going to be a lagging power factor because it will be an inductive reactance. Okay. So then you go to Busbar 3. Now Busbar 3 is now going to be a level switching, a stepping down, because now we have two transformers, 80 MVA transformer. Now remember, it's very important, the capacity of the transformer. Like here we got a 20 MVA transformer, which means this location here, you cannot switch something, you cannot power something that's going to draw more than 20 MVA. You're going to explode your transformers. So if you have a small city here, make sure your city can only take up to 20. Not even get there, but around 15. If your city start expanding, getting bigger, factories and school, you must change these transformers. So that's basically why we have these transformers here are 80 MVA. They are big. Because if you look at it, from this 80 MVA transformers, we are going to supply an entire system down here, which are separated by two different locations. Also remember that the system overall is supplying only 100 MVA. So you have to remember that the system is supplying 100 MVA. So you're not going to have a transformer that is rated more than what the substation is actually outputting. So moving on from Busbar 3, we have a transformer, and into Busbar, that's Busbar 1, that's 2, that's 3. This is Busbar 4. Now the system have been stepped down into a 66 kilovolt. So we move from 132 kilovolt to 66 kilovolt. So these substations here is a stepping down substation, and we have our switching here, isolators, and so this is just a representation. We can literally, this is an entire substation. There are circuit breakers in there, there are surge arresters, there's all sort of things there that need to be in a substation to ensure that there is protection of the power system. Now from this substation, we also have a location that is also taking power from there. That's equipped with two step down transformers that's stepping down to also 11 kV, also rated at 20 MVA. Then we move from there, from this Busbar 4, substation 4, and to the last Busbar 5 of the system. And we're still transporting, the power system is still sending a 66 kilovolt through the line. Now, notice now we have a different cable that is used here. Now the cable references now, they are not giving us the amperage, the rated current of the cable. They are now giving us the area of the cable, which is 3 times 710 millimeter square. Now, still using the table of reference, you can use this area, the value of the area, to approximate, to get the equivalent impedance and then multiply that impedance, which the impedance that the table will give you will be per kilometer. So you have to multiply it to the number of kilometer, which is 2.8 kilometers here. Now remember, this is 3. That means it's a 3-phase. It's a 3-phase system. Okay. Then we move on. From there, after you replace the impedance there, you'll have a different short circuit current here. Then you come to bus bar number 5. Okay, this is a mistake here. It shouldn't be 132 kilovolt. That's a typo. It is a 66 kilovolt because we're coming from a 80 transformer 3 and 4 that are stepping down from the 132 to a 66 kilovolt. So this bus bar, this entire line here is 66 kilovolt. Right here it shows location 4, 66 kilovolt. So this is your last bus bar, basically your last substation. You have your circuit breaker, you will have your relays, you will have everything set up there. You can see these are your current transformers that are monitoring the amount of current going in through here. So if the current exceeds, it's going to trip the circuit, send a signal to circuit breaker. That is an entire lecture tutorial we're going to make to explain how this system works. So basically that is it. You have now these transformers here rated at 40 MVA supplying into this location. And from there you have an entire system. Now you can provide a protection system, a downstream protection system that will be all the way up to the power system connection. Remember, if you use IDMT relays, you have to set up your discrimination so that every circuit breakers and IDMT used along all these bus bar, the total time must not be more than 2 seconds, because otherwise that will be too much to allow a short circuit current to last. It's going to destroy the power system. So that's how the things are set up, but we're going to go deeper on that in probably the coming tutorial. So that is basically how a 5 bus bar system is done. Hey guys, welcome back to this tutorial. This is a second tutorial on power system network design. If you like this tutorial or the previous one, please don't forget to like and share, give it a thumbs up and subscribe to my channel. That will be highly appreciated as we move forward. So in this tutorial, we are going to reduce this network diagram that we've seen previously. Now this is a representation of a network that can be implemented for a country or a city, anything. So this is basically a representation of bus bar that represents substation with transmission lines running down the line down to the last distribution center or the last load or consumer. So these are parallel lines. You can see they all rated exactly the same, with basically 2 lines running simultaneously. Now we're going to reduce these to a single simple diagram that we can work our calculations. So I emphasize, if you stick around, this is going to be focused on the protection of bus bar. These are bus bars, so we need to focus on how these bus bar can be protected, because you may have a lot of things being connected. For instance, you can see this bus bar number 2. We have a load that's connected here. That's an 11 kilovolt system that's going. We have a transformer. We don't know what's going to be connected on this bus bar, but we know it's coming from this bus bar 2. So we need to ensure that bus bar 2 got adequate protection to deal with whatever situation that might occur there. Even though this bus bar 2 itself need to have its own protection. So if you stick around, you're going to see various ways of how to make this protection possible in an electrical network design. This is the same process or procedure that are taken before anything is designed, from power station, substation to transmission line. Okay, so let's see what is the next step for reducing this network. We have now removed the parallel line that was going along with this branch, as you can see, and we've removed the load that were connected on some of these bus bars, as we're going to be focusing on the protection of bus bar, as we said before. Now you can see this substation here got the it's 132 kilovolt. That basically mean the generator that we have here is supplying a magnitude potential of 132 kilovolt. But then they say the generator, they have a per unit of 24%. That is important, because this 24% is what's going to tell us with the voltage what exactly is the power that is being delivered. Remember, just like your battery got an internal resistance, the internal impedance or resistance of the battery is what tells you how much power the battery can deliver based on its voltage. So this is basically the same. So the 24% is the internal impedance of the generator. So we're going to see how much power will be coming out of that generator. This number you see here is the maximum short circuit that can flow if there is a short circuit here. Stick around, you'll see how we get that. And there is a 4.5 kilometer line running with a back cable of 650. And we have the same there, a bus bar. Then there is a 80 MVA transformer. And we have another line here. And the 5th bus bar. So it's a 5 bus bar system. Now, look at these cables. Now this cable, they just give enough parameters, like the name of the cable and how long it is and the current rating. But how do we know what cable to put there, what the reference? Because remember, a cable is a wire. It's a wire, and it's a resistance. It must have an internal resistance. There is always going to be an impedance to it. So some clever people have already done the work for us. We don't have to suffer to try to find out what exactly are the parameters of the cable. So we're going to look at this table of reference. Now these are provided by the national standard for electrical system. So we have the name of our cable is Bear. The name of the cable is Bear. So we look at a table of reference and bear what are the values we need. So we've got R1 and X1. Now R1 is the resistance, X1 is the reactance. You know the impedance is made of a resistance and a reactance. It's an inductive impedance. Now, and the important thing to know also is these values and references are referenced per kilometer. So if you have 100 kilometer, then you have to multiply it per 100. That's basically how big your impedance is going to be. And that makes sense because a long transmission line is going to be more voltage is going to be dropped on the system. But that's a subject for another day. So that's what we have here. And these were tested. These parameters were tested on a 100 MVA per unit system with a 35-degree ambient. So basically not the typical winter. So if these parameters might change depending on the weather. So those values are for a 35 degrees ambient. So basically summer. So in winter you should be expecting different parameters. So the values can be changed, might be changing depending on the weather. Okay, so now you know where we got the values. So basically we're going to replace them. And moving on, that's what we do. And what I've done here, I've now replaced the bare cable with the impedance parameter. Now you can see this is a resistive part and this is the inductive part, and that's from the impedance, and we have to multiply it by the number of kilometers. And I've done exactly the same thing here at 4.7 and also here. Now you notice here we have something different. We're going to see, instead of having a name of the cable, we had the millimeter square. Now this is the area of the cable. Now going back at the same table, we can see that they also gave us the area in millimeter square. Now we just have to see which area corresponds to what we have here, which is a 710, and we found that the 662 is close enough, so we take the values from that and then we replace and we get this impedance here. Now when we multiply it, we now get this impedance here. Now these are now the final, this is now the final impedance value for this transmission line, and this one as well, because we've now multiplied it by the number of kilometers. Okay, so we can still simplify this diagram to make it more readable. I mean, you can see it exactly, there is an up and it's going downstream, so we can basically reduce it to something more easily readable. That is something like this. So we got now our one line diagram simplified. As you can see, we still have our 0.24 J, which is the internal impedance, as we've said, of the power station, this power station here. Now we have the impedance for line 1, and this is busbar 2. This is impedance for line 2, and this is our giant transformer, and this transformer is have a per unit old of 10.1%. Now this one is important. These parameters are given on the nameplate of the transformers. Now we're going to need this old per unit as we're going to be changing from whatever base these values were calculated to the new base of 100 MVA. The new base of 100 MVA that we're going to be calculating for our system. And this is bus 4. Now this is a step down transformer that's taking from 132 to 66, and we go to line 3 and then bus 5. Now we're not going to be dealing with this transformer. I've just included them just for illustration purpose. This is a load section, it's going into a load, but we're not going to be worried about that. We only concern on the protection of this bus bar. So each of these bus bars represent a substation, and you know what we found at a substation. At the substations, they are relays, they are current transformer, voltage transformer, line arrestor, and so forth. A lot of things, circuit breakers. So those are the things that you will be focusing and how to calculate and find them. Thank you for watching. Please, if you like this video, give it a thumbs up, and don't forget to subscribe to my channel so that you don't miss the next videos, and also share to your social media network. Thank you very much. Your support is highly appreciated. Thank you. Hey guys, welcome back to this tutorial on power system network design. If you haven't yet subscribed to CMTEQ channel, please consider doing so right now. In this tutorial, we are going to follow up from the previous tutorial. On the previous tutorial, we saw how we took a network diagram. A network that illustrates a transmission line from the generating station down to the distribution substation for consumers. We have taken that network and converted it into a single line diagram, where we've reduced it to an impedance diagram and to what we have today in front of our screen. So if you haven't watched those tutorials, you are more than welcome to look them up and see how we got to this network here. Just a quick recap. This is a generating power station with an impedance per unit of 0.24, that is 24%. Now the generator is supplying 132 kilovolt, so which means this first bus bar have 132 kilovolt potential. Then we have a first line, which is a transmission line, a cable. Then we took the parameters of the cable and converted it into an impedance. And then we have a second bus bar. Then we have another line, and we have a third bus bar. Then there is a transformer here that is now transforming from the higher potential to a lower potential. That is from 132 kilovolt to 66 kilovolt. And we have a third line here, and that's going into this load. But on Busbar 4 we still have another load, and Busbar 2 we have another load. We will be talking about loads in the coming tutorial. Now in this tutorial we want to focus on how to convert this impedance into per unit. Why is it so important to convert the impedance into per unit? Because we will use the per unit values to calculate the entire network impedance and determine what will be the short circuit current for each bus bar. We want to know what's the magnitude of the short circuit current on bus bar 1, bus bar 2, bus bar 3, bus bar 4, and 5. That way we'll be able to work out the type of protection that we need from each bus bar and the device that need to be selected in terms of current transformer, circuit breaker, and so forth. So let's dive into it and see how we're going to get these per unit values. As we have already said, G1 is supplying 132 kilovolt on bus bar 1. Now we have to convert the impedance with the base apparent power of 100 MVA. Now the generator already have a per unit that is given to us. Now we only need to convert this impedance here with a base of 100 MVA into a per unit values. Now we've already seen how to do per unit if you look into the previous tutorial. So the first thing to do for line 1 is to get our impedance, which is now in this form. That's a rectangular form, to convert it into the polar form. From there then, what is our Z per unit? Now there is a formula for Z per unit. Then we need to find our Z per unit for line 1. Now Z per unit formula says is equal to ZA over ZB. ZA, which is this particular one here, and ZB, which is the base impedance of the actual line. Filling up the formula, ZB is equal to 174.24 ohm. Since we already know what's the value for ZA, then we're just going to replace into the Z per unit formula. That gives us 0.011 with an angle of 73.82 J per unit. So that is now the Z per unit for this line 1. Now we're moving on to line 2. Now we're going to follow the same procedure. We got ZA, which is the actual impedance of line 2 right there. Then we convert it into polar form as we've done with the line 1. Then we use our formula for ZB. Now ZB remains the same because the main parameters for calculating ZB is obviously the voltage for the zone. So as we can see, the zone 1 and zone 2 have the same magnitude. So it's still 132 kilovolt on this bus bar. So ZB remains unchanged. Then we can quickly go ahead and calculate our Z per unit for line 2. Replacing the values in the formula give us this value here, 0.0113 with an angle of 73.77 degree J per unit ohm. So that's the value for Z per unit for line 2. Moving on for the transformer T1. Now the transformer T1, it's a bit complicated, but we've done it before. Now transformer T1, we can see it's a step down transformer. The transformer have a rated apparent power of 80 MVA. So that is going to be considered as our ZB old. Then the Z per unit old is 10.1. That is 0.101%. So moving on, so we got ZB new is 100 MVA and ZB old is 80 MVA. And ZB old is 132 kV and ZB new is 132 kV. So while it doesn't change old and new, because we can see that this transformer, the primary is 132, the incoming line here also is 132 kV. So both old and new are exactly the same value. Then we move on. Z per unit old is 0.101 J. Now moving on, we replace all the parameters into the Z per unit formulas. This gives us a Z per unit for the transformer of 0,126 J per unit. Converting into polar form gives us a magnitude of 0,126 with an angle of 90 degrees. The angle is 90 degrees precisely because the transformer is believed to be purely inductive, so the angle will be exactly 90 degrees lagging. The next step is then to find the Z per unit for line 3, right there. Now we now know that busbar 4, which is the potential that is supplying line 3, have now changed. Now we know that line 3 is being supplied from busbar 4. And busbar 4 have now a potential of 66 kilovolt because the transformer here converted from 132 to 66 kilovolt. So now we have to bear that in mind when we calculate this line 3 Z per unit. So what do we do there? As always, we convert our actual impedance into a polar form. Then the interesting thing now is our zone voltage, V base for the zone, is now 66 kilovolt. It's no longer 132 like in the previous bus bars. From there, we know the formula for ZB, and ZB formula is BB square over SB new, which is the base MVA that we are calculating the entire network. So we found a ZB of 43.56 ohm. Now we can then calculate our Z per unit, which is Z actual over ZB, and that gives us this value for Z per unit of line 3. That is 0,021 with an angle of 85.73 degree J per unit ohm. So this is now how you convert an impedance diagram into a per unit diagram. In the next tutorial, I'm going to replace all these impedances with the corresponding per unit that we just calculated from each line and the transformer here. And from there, we're now going to be able to determine what will be the short circuit current, the short circuit magnitude for each bus bar. Then we can then talk about what kind of protection and rating we need for the current transformers and relays and so forth. Please, if you like this video, give it a thumbs up and consider subscribing to CMTEQ channel. Thank you. Cheers. Hey guys, welcome back to this series of tutorial on electrical network design. If you haven't yet subscribed to CMTEQ channel, please consider doing so to never miss tutorial like this. This is tutorial number 4 on this series of tutorial. In this tutorial, we're going to focus on how to calculate the fault current, the potential fault current that might flow on this bus bar in case of a short circuit. Now, that is the main reason that we calculated the per unit values, because precisely they're going to help us determine what will be the magnitude of the fault current. Now, when we talk about the prospective fault current, is the magnitude of the fault current that might flow at any point in a circuit in case of a short circuit. So the purpose of this tutorial is precisely to determine the magnitude of the fault current on each one of these bus bars. That way, the design engineer that is designing the network will know exactly what kind of equipment and the rating to place to protect this bus bar and the equipment that it will be supplying in case of a short circuit. Because if the short circuit occurs because of someone accidentally touching the live pad, you want to protect that person as quickly as possible. Or if it's a faulty equipment, you want the equipment also to be protected to minimize the cost of repair. Okay, now as we may know from the simple principle of Ohm law, the current depends on the resistance of the path the current is taking. So for a higher resistance, the current will be small. Now, the per unit value here, which was an impedance that we have converted back to a per unit value. If you look at the past videos, you'll see how we did that. So this per unit value will represent almost a resistance to the current flowing. This is why we're going to use it to determine our fault current that's going to be flowing to busbar 2. But before, the fault current at busbar 1 will solely depend on what the generator is supplying. Now the generator here, I've explained it already on the previous tutorial. The 0.24 is like an internal impedance, an internal resistance of either the battery or any power supplying device. Now these internal resistance determine what is the maximum power that the device must deliver. So in electronics design, for instance, if you are designing a power supply, you have to make sure that the overall impedance of your supply is low so that there is maximum power transfer. Because if your impedance, your internal resistance is high, you're not going to have maximum power transfer. There will be losses due to the internal resistance, because whenever you want to pass a current from point A to point B, you know the current is going to have to pass through this point here. And the maximum current that's going to get from A to B depend on what happened here. Now this is almost like your battery. Now this is the internal part of your battery. Now to ensure maximum power transfer from A to B, you have to make sure that there is less resistance inside here, so that you can get all the power to B. This is why it is important for your power supply or your battery to have an internal resistance that is almost negligible or that is very low. This is why you have this per unit here, which represent an internal resistance of the generator is very low. This means then that per unit value will determine how much current we're getting at that busbar 1. Now let's see how much current we're going to get into busbar 1 from that per unit value. As we have said, 0.24 J per unit is the generator internal impedance. Then we use a common formula that is used to determine the per unit current. Remember, on the previous tutorial, we've said I per unit is equal to 1 over Z per unit. 1 being represented by the 1 volt per unit, because in the per unit system, as the names implies unit, so we are dealing with 1 only. That's why everything is represented in a percentage value. That must be below 1. That's why it's called per unit. So moving on, as we already said, 0.24 J is the internal per unit of the generator. And using the per unit formula for the current, I per unit is equal to 1 over 0.24 with an angle of 90 degrees. Now this is the formula to calculate the per unit current. The 1 here represents the 1 volt per unit. Please look at the previous tutorial where we introduced that formula. This gives us a current of 4.166 amp. Now that is the per unit current. This is not the short circuit current. This is the per unit current in terms of percentage from a 1 volt per unit perspective. In order for us to get the short circuit current, we need now to multiply the I per unit times the I line, which is the base current. Now the base current is the current. Now if this is a 3-phase generator, the generator must have 3 phases here. So each phase is bringing in a current into the bus bar here. That's what we call the line current or the base current. Now to find that current, we use this formula that is on your screen. So we replace the value, then we get the current of 437.386 amp. That is our line current. As we've already said, the to get our short circuit current, we need now to multiply the I per unit times the I line. And that gives us 4.166 times 437,386. It gives us about 1.8 kiloamps of current. Now this is the maximum short circuit current that's flowing in this bus bar. So from the generator to this bus bar down to earth, there will be a 1.8 kiloamps of current. Now if you drink too much red wine and you think you can go touch that bus bar, remember there will be 1.8 kiloamps of current with a potential of 132 kilovolt flowing from your hand through your heart down to earth. And you don't want to know what will happen to you. Please don't do that. Now moving on, we may also calculate the short circuit MVA. Using our short circuit current, we can then calculate the short circuit MVA, which gives us a 416.6 megavolt ampere. Now, you'll notice that this is the MVA. Remember, this is the base MVA, so that's the total power the generator is supplying in this case. Now, if we take this line current here, we replace it in this formula, we should be able to get the same 100 MVA. Now, to calculate the short circuit MVA, we now use the short circuit current into this formula to get the value of the magnitude of the short circuit MVA. Now, moving on to busbar 2. Busbar 2, we're going to follow the same process. The process is of calculating the total impedance that is on the path to where the current is flowing. Now the current is now going to be flowing from the generator down to this bus bar, down to the line 1 and to this bus bar here. So we want to know what is the magnitude of the short circuit current on this bus bar. Just like we have explained, the generator acts like an internal impedance of a battery. Now to move power from point A to point B, you need to ensure that between A and B, you have minimum resistance so that your maximum power on the input will be maximum power on the output. This basically means we need to add the internal impedance of the generator plus the per unit here of the line, and these together will be the Z per unit total that will determine how much per unit current we're going to get for the system. So let's see how it works. The total per unit impedance from generator to busbar 2, that is from generator 1 to busbar 2, will be Z per unit of the generator is 0.24. Z per unit of the line is equal to 0.011 with an angle of 73.82 degree J per unit. This is a polar form. We convert it to the rectangular form. That way it will be much easier to add it with this one. We may also convert this to polar form and then we add it together with the polar form impedance of the line there. Moving on, the total Z per unit flowing from the generator to line 1 will then be equal to this, and that gives us a total Z per unit of 0.251 with an angle of 89.3 degree. Now we're now going to use this Z per unit total to determine what will be our I per unit. The I line will remain exactly the same. It doesn't change because we still have the same line that's running from the 132 kilovolt. So imagine if we're working from one single phase, we will have exactly the same phase running on the transmission line. This is why our I line will not change. Then we calculate our I per unit, which is now 1 over Z per unit. Now Z per unit is now this total Z per unit that we found of J024 plus this one, so that it gives us 3.984 amp. That's the I per unit. Just like we've done here, we now need to multiply the I per unit times the I line. We're gonna do exactly the same thing there. So I per unit times I line does give us the short circuit value of 1.742 kiloamps. So that is the maximum short circuit current that is flowing at this point, busbar 2. Okay, now we may also calculate the short circuit MVA from the same busbar, and that will be about 398.4 megavolt ampere. That is, we use the same process that we've done here to determine this one. We do exactly the same. Instead of using the line current, we now use the short circuit current here, and we found this. So we're going to stop this video for now here before it gets too long. In the next tutorial, we're going to do busbar 3, busbar 4, and busbar 5 to close the tutorial part 2. So please stay tuned, and don't forget to give it a thumbs up and subscribe to my channel for future tutorial like this. Thank you. Hey guys, welcome back. This is part 2 from tutorial 1 on how to calculate the maximum short circuit current available at a bus bar on our series of electrical network design. If you haven't yet subscribed to CMTEQ channel, please do it right now to never miss videos like this. In this tutorial, we're going to continue from where we left off. That is to determine the current that must flow on busbar 3, busbar 4, and busbar 5. We've already determined what's the current flowing on busbar 1 and busbar 2. You may look at the previous tutorial to update yourself. So let's get right into it. What will be the maximum short circuit current at busbar 3? We've already seen from the previous tutorial that we need to add all the per unit impedance from the generator to line 1 and line 2 in order to get what the current will be on busbar 3, as the current will take this particular path. So the total per unit impedance will be the sums of Z per unit of generator of line 1 and line 2 as shown below. And adding those, we will have the 0.24J and 0.011 with an angle of 73.82 and 0.0113 with an angle of 73.77. Now in the previous tutorial, we have converted these ones that are in polar form into the rectangular form. This time around, we will convert this one into polar form. As you can see, there is no real part, it's only the imaginary part. That means the angle is 90 degrees. So we convert it into polar form, and that way we can just add it easily with our calculator. So the sums is then equal to 0.261 with an angle of 88.64 degrees. So this is the total per unit impedance from the generator down line 1, down line 2, and flowing down to busbar 3 to earth. Now this is the path the current flowing from the generator will take. This means this total per unit is then what we're going to use to calculate our I per unit current. I per unit current will then be given as 1 over 0.261 with an angle of 88.64. We found an I per unit of 3.83 with a negative angle, because the angle will now move to the top and change the sign and become a negative angle. But we're not going to take account of that. We're just concerned about the amplitude of the current, which is 3.83. Now the line current will remain exactly the same as the busbar voltage haven't changed. We still have 132 kilovolt. So we're going to use exactly the same line current, which is 437.386 amp. The previous tutorial, we saw how we calculated that line current using the formula on your screen. Moving forward, then the I short circuit will be the I per unit times I line. Replacing the formula, the values into the formula, we get 3.83 times 437 amps, and that gives us a total short circuit current of 1675.118 amp. So this is the current that will be available at this point. So if someone has to come and touch here, that's the current that will flow from that bus bar into the ground. Or anything has to happen to cause that short circuit to take the shortcut. That's what it called. It takes the shortcut instead of going down this way. It's now take the shortcut straight to earth. So that's the magnitude that will be available. That 1.6 kiloamps. Moving on, we may also, as we have seen, calculate the total short circuit MVA that is available based on that short circuit current. That is basically replacing the current into this apparent power formula. That will then give us a value of 383 megavolt ampere as the magnitude of the prospective short circuit MVA. Now moving on, we go to busbar 4. What is the maximum short circuit current that will flow at busbar 4? Right there. Now the current will now take this path this way. So this means our Z per unit total here must now include the per unit value of the transformer T1. Remember, this per unit is the one that is found as an internal impedance per unit of the transformer. Now there is something that's going to be different here this time. What is it? Now we can see that this bus bar is now energized with a different voltage. The potential have changed. The potential is no longer 132 kilovolt. It's now 66 kilovolt, since the step down transformer here have done its work. So what does it mean? That means the line current will now be different. The line current will change. It's no longer going to be the same. It's going to increase. You guessed it. The voltage goes down, the current must increase to maintain the kVA in and kVA out. So the Z per unit total will then be the sums of all the per unit values in the line. That gives us a Z per unit total of 0.387 with an angle of 89.1 degree. Calculating our I per unit from the Z per unit total will then give us a value of 2.584 with an angle of minus 89.1 degree. As we've stated, we only concern about the amplitude, the magnitude of the current there, which give us a value of 2.584 amp. So moving on, I line will increase as the voltage have now been reduced due to the step down current. So now our I line is no longer going to be 437. We have now to calculate our I line. So we calculate our I line with the I base formula on your screen. Remember, I line is equal to I base. That is the base current that it will be flowing on the secondary of the transformer here. Because now this is a primary and this is a secondary. So our I base is now going to be on the secondary. Remember, for a step down transformer, I1 is not equal to I2. So if it's a step down, you're going to have a low current there and a high current here. Okay, so now our I line is going to be with the same 100 MVA with a new voltage. Then it's going to be 874.77 amps. So that is now the value of our line current. Continuing on our fault current at busbar 4, we've already calculated I line, which is 874.77 amps. This means then the short circuit current at busbar 4 is now I per unit times I line. We already got our I per unit, which is 2.584. Now multiplying it with our I line then give us a short circuit current of 2260.387 amps. That's 2.2 kilo amps. So that is about 2.2 kilo amps that's going to be present at this point here. So if something has to happen here, or someone drinks a lot of red wine and come and touch his busbar at the substations, he is going to be electrocuted with a 2200 amps flowing from his hand through his heart down to earth with a potential of 66 kilovolt. You don't want to know what will happen to that person. Okay, so we move forward. We can also calculate the short circuit MVA using the same method, replacing our I line into the formula. Then we get a short circuit MVA of 258.4 megavolt ampere. Now we move on to fault current on busbar 5. That is this busbar 5. Okay, now the same procedure will apply. So the current will now take this path. So this is only possible if there is no short circuit here. Now the current is no longer going there. Now the current has to now pass through this impedance here, Z per unit, line 2. Now this is line 3. That's a typo there. So that is Z per unit, line 3. Because that's line 1, line 2, and that is line 3. So now the current will now take this path right there. Now what will be the Z per unit total? We just have to add all the per unit from the generator, Z per unit of the line 1, line 2, transformer, and now line 3. So we add all of them into polar form and we get a Z per unit total of 0,408 with an angle of 88.9 degrees. This Z per unit total will then be used into the I per unit formula, which is 1 over Z per unit total, and that gives us a current of 2.451 with an angle of minus 88.9 degrees. So now that is the I per unit up to this point, the value of the I per unit. Now we need to multiply it with the I line. Now remember, at this point, I line is also going to still be the same because we are still operating at a 66 kilovolt. There is no more transformer at this point here. So then our I short circuit is going to be 2144.04 amps. That is our I short circuit at busbar 5, this point here. Moving on, we may also calculate the short circuit MVA. That is going to give us a value of 245.1 megavolt ampere. So this is in short how you calculate the short circuit current of a particular network for every busbar involved in a particular substations or on multiple substations to that meter. Now that we've already determined what are the maximum short circuit current for each one of these busbar, please notice the patterns here. We had a higher voltage here, so the current was slightly smaller. Now as the voltage went down via this transformer, because remember there is a transformer at this point here. Now there is a transformer here. There is a transformer there that is changing from 132 kilovolt to 66. So now we can see the voltage go, the current go up. So the current goes up as the voltage goes down to maintain transformer power transfer properties. Okay, so in the next tutorial, that is what we will be doing. How to select these current transformers here. Just current transformers here, because now we know that these protective current transformer or measuring current transformer, whichever the case may be, they are going to be protecting whatever equipment that is here or what is connected onto these bus bars, these loads here. So this current transformer must be able to know if what's the normal current that's flowing here, and in a situation where that current is no longer the same, now it's a short circuit current, the current transformer then need to tell the circuit breaker, listen, the current value is no longer what it's supposed to be, so you need to break. And the circuit breaker is going to break, open up, and protect the equipment or the personnel. So that's what we're going to do in the next tutorial. Please, thank you for watching. Subscribe to CMTEQ channel, like the video and share, and stay tuned for the next tutorial. Thank you. Cheers. Hey guys, welcome back to this series of tutorial on electrical network design. In this tutorial, we will briefly look at the process of how to select a suitable current transformer that will be able to provide adequate protection for our short circuit current on this busbar and all the other busbar as we have seen. In the previous tutorial, we saw how to calculate this short circuit current. There is a process that is involved for getting them. So if you haven't watched those tutorials, please look on the description below. There is a link for those tutorials. And if you haven't yet subscribed to CMTEQ channel, please consider doing so right now and hit the bell to stay up to date with new tutorial. Thank you in advance as you going to hit that button. Okay, so what is a current transformer? A current transformer, as we see here, this is basically a physical representation sort of, but this is an electrical symbol. Now, current transformer is a measuring device. Whether it is used for protection or metering, it is a measuring device that is used to safely reproduce a low-level current that accurately represents a high-level current for the purpose of protection and metering. So the high-level current will be the current that will be passing through here. So this could be our busbar. That is a primary current that will be flowing there, and that primary current will be proportional. Now the secondary current that will be passing here, IS, will be proportional to IP, which is a primary current. So it could be just the load current that is flowing, a normal current, or it could be the short circuit current, but it should be proportional to what we will be getting here. Now, how does this process take place? Now, according to the process of transforming the current, obviously, now this is the same process as normal transformers work, a voltage transformer, that work in the phenomena of electromagnetic induction. Now, according to Ampere's law, together with Maxwell equations, it says that if a magnetic field is integrated around a closed loop of wire, the value of that integral is equal to the net current enclosed by the loop of the current transformer. So this basically means the current that is going to be produced based on the magnetic field that is produced by the primary current will be a representation of the current that is passing through here. That's in short what these equations entail. Now there is a lot of literature around that. The scope of this tutorial is not on that. We will be doing some tutorial on those in the coming days. Okay, now moving forward, the current on the secondary is directly proportional to the current flowing through the center of the core. Now what is a current that flowing through the center of the core? That is IP. So this is a core. Now the current flowing through the center of the core is our busbar current. Now this current on the secondary IS is proportional to this current. So you just have to work in terms of the ratio. This one is going to be a small one. The number of turn here will determine how much you get here. That's where our turn ratio comes into the equations. So for example, for a 1000 to 5 ratings, that means you have 1000 the primary 5 amps rating or 200 to 1. This means a 1000 amp flowing on this core here on the primary will produce a 5 amp here on the secondary, and that 5 amp will be able to be measured by this ammeter that's connected here. In our case, this is going to be a protection current transformer, not a metering one. It will be a protection one because it needs to send a signal to the relays, and the relay need to trip the circuit breaker. So in this case, the protection CT must be used in combination with a tripping device like our IDMT and the circuit breaker to trip the breaker when there is an overload or a fault on the system, as we have seen in the previous tutorial. Now, the current transformer must step down from a high primary current to a low level current. Those basically mean, as per transformer properties, since the current is going down, the voltage must go up, okay, to maintain the kVA in and the kVA out. So you have to maintain the power in must be the power out. So as your voltage, your current is stepping down, so the voltage must go up. So VA in must be equal to VA out. So we've seen that already. So this is why it's not safe. So because the voltage is going up there. Now imagine you already have this busbar here that's got 132 kilovolts. So potentially you have 132 kilovolt on this on the primary of these current transformers. Now because now the current is going down, so the voltage is going to increase. That means the 132 kilovolt could be several hundreds of kilovolt on the poles of this current transformer. So what does it mean? If this is left open, for instance, if there is no current transformer here, I mean if there is no ammeter here, this is open, you come and touch there, that's what you get. You're going to get probably 5 times this, depends on what the ratio is here, and that's going to shock you. So this is why if this is not being used, you have to short it with a wire or a jumper. Never leave a current transformer open circuited. Even if it's a small current transformer, it's a very dangerous leaving it open circuited. Now, there is also an important property of the current transformer that's called a knee point voltage. Now, the knee point voltage means that when the CT operates, as you can see here, this is the voltage and this is the current. So this is a voltage, that's a current, and if you can see, this is very linear. So it's following, okay? Now, outside this point here, it's no longer following. It's no longer linear. You can see there is a curve now. That's why it's called a knee point voltage. So when the CT operates outside, it's a rating. That's when we get to that point. Because once we are in this point, as long as we are in this region here, we are operating within the rating of the current transformer. But suddenly when a high current that exceeds the rating start to pass, we get out of the linearity region. We get into the knee point voltage region. So this happens when the output current stop following the input current. So we know that the output current, which is IS, is following what the input current is doing. So it's linear. But now when the output current stop following the input current, we now reach the saturation region, this region here. So we're no longer in the linear zone or the good zone. We're now in the danger zone. Why is it a danger zone? Because it doesn't matter what that current is now. The output will no longer going to give an accurate representation. We could be having 100 million amps there. This secondary IS will not going to tell us what exactly is that current. So there is protection is lost. So you don't have your protection anymore. So that's what we call a saturation region. When the current transformer get to that point, it's become useless because it's not protecting anymore. So the purpose of the protection is to ensure that as soon as we get out of this linear region, once we get to the knee point voltage there, your system must have tripped already to provide protection. Because if it failed to do that, then you know your protection is not working. So now we move on to see how we're going to determine the turn ratio for our transformer. That must be according to the magnitude of the fault current that we have on each one of these bus bar. So then our current transformer ratio must be determined using the calculated fault current that we have on each of these bus bars. Now, this is to ensure the protection of the transformers. Remember, in this case of bus bar 3, we have a transformer here that's converting, that's stepping down from 132 to 66 kilovolt. So we need to protect the transformer in case there is a short circuit on the bus bar. So this CT ratio will be important in order to ensure the protections of the transformers and other equipment that are connected onto the bus bars. So the current transformers selected here have to be able to protect our transformers and other equipment that are connected on the bus bar. Now there is another property of the current transformer that is called accuracy class factor or accuracy limit. Now in this series of tutorial we have selected the accuracy factors of 10p10. Now what that means is we are providing a 10% maximum accuracy limit of error. So which means the measurement that we're going to be getting at the secondary will be plus or minus 10% the actual representation. So that's what the 10 means. Now the other 10 means that our rated primary current must be multiplied 10 times. So that's actually what it means. It's 10 times the rated current. So what it means is instead of having a ratio of 1822 to 1, so basically that's the primary current and that's what the secondary current. Now the tens will then divide the rated current by 10 to give us 182 with a ratio of 1. So that way you can get a smaller current transformer rather than getting a big one that will take all these turns ratios here. So you're going to get a smaller current transformer. But now you're not going to get a current transformer that gives you exactly this 182 to 1 ratio. So there are already current transformers that's got standard values of current transformers that's already designed and being sold by manufacturers. So for instance, for 182, you're going to get a 200 to 1 ratio. Now this is a standard CT ratio. So that is what you're going to select it for the particular bus bar. So your current transformer will give you a ratio error of 10% based on what the accuracy limit factor that you choose. That is regardless. Even if your fault here reach 10 times this value that you have, you're still going to get a 10% accuracy of error. And you know, as we've seen previously, so the CT will then reach a saturation and it will basically become useless. So that is a very important factor to remember. And so that 10% margin of tolerance will actually even ensure more reliability for your selected current transformer. And reliability is very important because you don't want to be sending false triggers into your relay coil, and that's going to be tripping your circuit breaker even if there is no fault. So you need a reliable system. So the margins of accuracy is important. So that is basically what you need in order to select your current transformer. There is a lot more that can be said about it. So based on that, we then have the selected current transformer ratios based on the particular current on every one of these bus bars with our selected accuracy factor limit. So before ending this tutorial, let's just see how this system actually operates. So in case of a fault here, you're going to have a large current flowing. Now this is our current transformer. Now the current transformer, based on your ratio, you're now going to have a current that will be present here at the relay coil. Now the relay coil is now going to be energized. So if that's a 1 amp nominal relays, now you've now reached your short circuit current. Now you got a 1 amp now flowing here. So now the relay is going to trigger and the contact will pull, and that's going to close this circuit here. Once the circuit closes, you now have this DC source that's already ready here. That's now going to flow like this. Now that's going to flow and create a current that's going to flow on the coil, will energize that coil again, and the coil will now trip the release mechanism of the circuit breaker. So that's basically how this entire system works. That's what we're going to implement here by selecting a proper short current transformer and IDMT relays and the circuit breaker. That's what we're going to achieve, the same operation right here. So that's basically how protection are ensured on bus bars. So this is a fundamental. There is a lot of things like there is new technologies that are coming on now. You can include intelligence devices and other various apparatus, but here what you see here is the fundamental of busbar protections of your network system. So guys, if you like this tutorial, you found something useful, give it a thumbs up and don't forget to subscribe to this channel. Also leave your comment down below the comment line. Anything you want to ask, we will gladly answer to your comment. Thank you for watching. See you in the next tutorial. Cheers. Hey guys, welcome back to this tutorial on electrical network design. In this tutorial, we're going to see how to determine our plug settings. As you can see, we have a 5 bus bar arrangement, and on the top bus bar we have a line that is rated at 132 kilovolt flowing downstream. A second bus bar also have 132 kilovolt, and then the third bus bar at the same potential level. On the fourth bus bar we have a 66 kilovolt. This means between bus bar 3 and bus bar 4 there is a transformer here, and so forth until bus bar 5 we have a 66 kilovolt, and from there we can have feeders going into 11 kilovolt lower voltage for distribution. Okay, and if you haven't watched the previous tutorial, please go and have a look so that you can see how we arrived to this diagram here. And we saw how to determine these current transformer ratios. As you can see, this current transformer here have a ratio of 201. This one have a ratio also of 201 and so forth. And the last one here have a ratio of 251. And that is based on the current, the fault current available on the bus bar. Okay. So what is the story here? The story here is you have an IDMT relay, right? That is right here. And the IDMT relay need to send a signal to the circuit breaker, and the circuit breaker must trip. But the IDMT relay itself need to receive a signal based on what the current transformer is seeing from the current that is flowing this way. Okay. But now the IDMT relay must operate based on the settings that are set on it. And I have a tutorial that I did on the plug settings of an IDMT relay, how to find them. You can look the video on the description box. Get yourself up to date. Okay, so in this tutorial, we're going to see how to determine the plug settings for this IDMT relay so that they can react on time when there is a fault current available. Okay, now before we continue, please hit the like button and subscribe to CMTEQ channel so that you never miss more tutorial like this. I thank you for that. Okay, now what we're going to do first is to arrange this network into an arrangement that is going to be facilitating us to calculate our IDMT relay settings. Okay, now reconstructing the following diagram so that we can calculate our IDMT relays plug settings will look something as follow. So here we can see now we have our 5 busbar arrangement laid out in a different way to facilitate the calculation of the IDMT settings. So now we're going to work from the lower relays to the upstream relays. That way, the relays at the bottom, that will be thus relay number 4 here, we'll be looking out at the fault that is going to be available on busbar 5, and relay 3 is going to be looking out for a fault on busbar 4 and busbar 5. Relay 2 will look out for the fault on busbar 3, busbar 4 and 5 and so forth and so forth. So this is why it's better to lay them out like this, and then you can see clearly. So now the plug setting we are looking now is for the relays as follow. The relay need to get a signal from the current transformer as I've already illustrated there, and that signal then must be sent into the circuit breaker to trip the circuit. Okay, but now the key element in order to determine the plug settings for the relays is the current. Okay, the load current that is going to be flowing into the relay, because just like a circuit breaker, there is a normal current that is flowing when the circuit is operating. Okay, so that current is the load current. So the relay must not trip when that current is passing, because that's a normal condition. The relay must only trip when the current passing through it exceeds the load current. In that case, it could be the fault current or something a little less than the fault current, depending on where the fault occur on your network. Okay, now without any further delay, let's go ahead and calculate the plug setting, that is PS4 for relay number 4. Now, as we have said, relay number 4 must look at the load current that is going into busbar 5, and the load there is said to be 40 MVA. We don't know what type of load is there, but we assume these are normal load conditions. So we assume there are no motors or anything that can sky high the current, but we assume it's just a normal load. So it's 40 MVA. So in that, we can then calculate the load current based on that. So the plug setting for relay 5 with a load of 40 MVA will then mean, if we know that S load is VL times IL times square root of 3 in a 3-phase system, then our load current is given by the formula below. Then our load current is given by the following formula, and from there we can then deduce the load current is 40 times to the power 6, that is 40 MVA, over the square root of 3 times 66 kilovolt. Now the 66 kilovolt is the busbar voltage, the busbar potential that we have there, and that is 66 kilovolt on this busbar here, busbar 5. Okay, and that gives us a load current of 349.91 amp. So that is now the load current that is flowing through this relay in a normal condition, and it shouldn't trip from that. So we're going to set the settings for that. So that means then the formula to calculate our plug setting is then given by the following. So our plug settings for the relay is equal to I load divided by 0.9 times the CT ratio. The CT ratio is the current transformer ratio. For this one here, relay 4, the current transformer attached to it got a ratio 250/1. Okay, now the 0.9 means that the normal full load current must not exceed, okay, 90% of the relay settings that we're going to set. Now, if this condition is not met, then after a brief period of overload, okay, if there is an overload, now which will then cause it to start turning slowly, okay, so the relay will not reset to its initial position after the load current return to normal. So this is why we have to have this 0.9 set up. Okay, so that we can make sure that the relay continue to operate under the normal condition, doesn't trip. Now the next thing to do now is we know what the load current is, what our CT ratio is. We can then calculate our plug setting for the relay by replacing. Now the plug setting for this relay 4 will then be 349.91 over 0.9 times 250, okay, and that gives me 1.56, okay. 1.56 is the settings for the relay, but they are standard values that we can select on. Now the plug settings, as you can see, we have discussed it on one of the videos that I made. So there is a tapping that we can go to select which tapping from the coil that we can take that make the coil to be energized depending on how much current flowing. Okay, so now these are the standard tappings. We got 50%, 75, 100, 125, 150, 175 and 200%. And you have to choose from the value that you get here, but you can never choose something lower. So for instance, here we have 1.56. So in terms of percentage, this means we have 156%. As we can see, we cannot take 150. That means we are going lower. We must always go higher. Then we have to take the next tapping, which is 175%. So our relay setting will then be 175% for the following relay PS4. Okay, now continuing to the next plug settings, that is for relay 3. Now, before we do that, I would like to mention again one small detail on the 0.9 here. There is a situation where you are dealing, let's say the loads here are motors, okay? If the loads are motors, we all know that motors, they got a high starting current before the current can stabilize. Now, in that condition, you have to use 1.1, that is 110% of the relay setting current. So you can see that 110% of the setting current is rated slightly higher, but that is to take care of the high starting current in case of motors. Other than that, if you are dealing with normal loads, you just have to stick with the 0.9, okay, which is 90% of the setting current. Okay, now let's carry on here for plug settings for relay 3. Now, plug setting for relay 3, that is this relay here. Now, we know that this relay here is supposed to be looking at the loads, that is the 40 MVA and the 20 MVA for both busbar 4 and 5. But no, there is something else here, something different in this relay 3 here. Why? Because if we come back to this diagram here on the left, busbar 3, on the previous tutorial, we know that this busbar here, busbar 4 is 66 kilovolt and busbar 3 is 132 kilovolt, pardon me. So which means there is a transformer here that is stepping down. So there is a transformer there that's stepping down from 132 to 66, and that transformer is exactly at this point here. So there is a transformer there that is stepping down, okay, and that transformer is rated at 80 MVA. You have to look at the previous tutorial that we saw, tutorial 1 and 2, where we needed to convert the network into an impedance diagram. There we discussed the transformer rating there. So from there, you know that since the relay is on the primary, so there is a primary and this side is a secondary, because that's a 66, that's 132, the relay is right on the primary side of the transformer. That means this relay is only seeing the current that's going into the transformer, that is the primary current of the transformer, not the current that is on the secondary, which will be the current feeding into these two bus bars. So that will mean this relay here does not see the amount of fault that goes, or loads current that goes into this bus bar. He only sees the line current or the primary current going into this transformer that is here at this point. before the 66 kilovolt point. So having said that, that means then we're going to determine the load current for that relay as the primary current of our transformer. Okay, so the transformer is rated at 80 MVA. That will then mean our I load will then be equal to 80 times 10 to the power 6 over square root of 3 and 132 kilovolt. And that gives us 349.91. So that's the primary current going into the transformer there. Okay, it doesn't matter how much current there short circuit, but the transformer can only let go what its primary allow it to go, because that's the rating. So that is our load current for relay 3. Now, so from that we can then deduce our plug setting for relay 3 is going to be 349.91, 0.9 times 200, and the 200 is a rating, the ratio of this transformer. So that gives us 1.94, and from our plug settings standard values, we know that this is very close to 200. So this then means our plug setting for relay 3 will then be 200%. Okay, so now we found the plug setting for relay 3, relay 4. The next thing to do is then the plug setting for relay 2. So moving on, we can then calculate the plug setting for relay 2. Okay, and once again, relay 2 is only going to see the load current as the primary current that is flowing from here all the way down to the primary current of this transformer that is located here. Okay, as we have seen there, the transformer is located at that point. So which means this relay here, that is now relay 2, is also going to see exactly the same current that is flowing down here to that transformer. So which means relay 2 is going to have the same load current as relay 3, which we have already calculated, that is 349.91 amp. Okay, so from there we can then determine the same plug setting for the relay of 1.94, which gives us a 200% plug setting for this relay, since they have the same ratio as well. Okay, now the next one is to calculate the plug settings for relay 1, PS1, the plug setting for relay 1. Okay, now it gets a little interesting, because even though we still have the same primary current that is flowing there, but now remember, there is something else attached to Busbar 2. There is another load of 20 MVA here. So that load is also being seen by this relay 1. So which means we're going to have two currents. So one current is going down this way and one current is going down that way. So it's splitting. Okay. So we cannot say that because there is a 349.9 amp that's going on there, so the other current is going down here, that means there will be less current there. No. There is a 349 amps that's flowing this way. So that will mean there is another current that's flowing here. So which means at this point here, there is going to be a much bigger current here. That must be something around 400 amps of current, because it needs to split, one going down there, the other going this way. So in that way, we're first going to calculate the load for the 20 MVA load attached to Busbar 2. Okay. And then we're going to add it plus a primary current of transformer 1. So that will mean the load for our Busbar 2 with a 20 MVA load with 132 kilovolt, because the Busbar here is 132 at that point there. And we get a current of 87.48 amps. And from there, we have I load 2 that is going this way, and that gives us 349.91 amp. So we have two loads current that we then need to add, because that is the big I that is flowing through this current transformer that this relay is supposed to get a signal from. So from there, we then have a total load current of 437.39. So that is the current at this point, 437.39 39 amps that's flowing here. So the splitting at this point, 87 is going down this way to feed this load here, and the 349 is going this way to the primary of the transformer to feed these other loads there. Okay, so from there we can then calculate our plug settings by replacing the current. We then find a value of 2.43, and from the standard values we know the highest is 2, that is 200%, so we can't go any lower or any higher. So that is 200%. That will be the plug settings for relay 1. Okay, so thank you guys for watching this tutorial. Please, I will appreciate a thumbs up and subscribing to CMTEQ channel. Hit the bell for more tutorial like this. In the next tutorial, we then going to see how to calculate the timings for these relays. When must they trip? When something abnormal happens. Since we just determined the plug settings, the next thing is now the timing for them to trip. Thank you very much. Stay tuned for the next tutorial. Cheers. Hey guys, welcome back to this electrical network design. Now this is tutorial number 7. In this tutorial, we're going to see how to calculate the timing of these relays. So we got 4 relays, 1, 2, 3, 4, that are protecting each one of these 5 bus bars. Okay, now before we do that, I'd like to make a quick recap on what we've done so far. So we started off from tutorial 1, where we took a power network, okay, that was designed for a particular location, a new location. Then some electrical engineers are called upon to design the network. So we had cables, length that were determined and so forth. Then we needed then to take this network here and convert it into an impedance diagram. As much as we can get the power network laid out, there isn't much we can do if we don't get into the details of the cables, the impedances, because that is what is important to complete the design of the network. So we went ahead and did the impedance diagram. Now the impedance diagram, as you can see here for line 1, now this Z line 1 is a representation of the cable and the impedance and all the elements that make part of that cable, and of line 2 the transformer and so forth. So we did a tutorial to convert that power network into an impedance diagram. And we went ahead into tutorial number 3. We then needed to determine the per unit equivalence for our impedance diagram, because you have to take the impedance diagram and convert it into a per unit diagram. That is one of the process you have to do if you need to calculate your fault current or your per unit current. And that was tutorial 3. Now tutorial 4, we were dealing on the bus bar fault current. As you can see, the maximum fault current that every bus bar is going to be dealing with in case of a short circuit. So that's what we were dealing with tutorial number 4. Then we move into tutorial number 5. Tutorial number 5, we dealt with current transformers, because you need to select the current transformer that must protect your bus bar in order to protect in case of a short circuit current. So you need to protect your bus bar. So in tutorial 5, we saw how to select that current transformer, and we went into some of the theory behind the working principle of the current transformer. Then we moved on to tutorial number 6. Now tutorial number 6, that's where we needed to complete then the remaining element for our network. That was the plug settings. So the plug setting, we did them for these IDMT relays. They needed the plug settings in order to prepare to calculate the tripping time for the IDMT relays. So that was tutorial number 6. We did the IDMT relays. So you have to update yourself and really take time to watch all these tutorials so that you can understand a solid understanding of how an electrical network is configured, designed, and all the elements that are necessary to ensure a reliable working electrical network. Okay, so in this tutorial, we're going to focus, as I said earlier, on calculating the tripping time of these IDMT relays. Now, there are important terms that one must take note when calculating the IDMT relay tripping times. Okay, and those terms are the TMS. Now, that's the time multiplier settings. Now, I did a tutorial on IDMT relays, just the basic principle how to test an IDMT relays and plot the characteristics curve. So you can find the link for that tutorial on the description box. Now, if you watch that tutorial, you'll understand exactly what do we mean by time multiplier settings. The other important factor is obviously the actual tripping time that your IDMT is supposed now to trip. And then we also have TC, that is the operating time. So you got TA and TC. And then the last element is the multiple of current setting or multiple of setting current. Now, these elements, you have to keep them in mind, and you actually need to understand what they are if you want to understand how to calculate these IDMT relays tripping time. Again, you can go ahead and watch that tutorial I did on IDMT relay to get some further understanding. Now, when calculating the tripping time for your network protection, you need to work from down up. So as you can see, these are circuit breakers. So you got circuit breaker 1, 2, 3, and 4 that are linked to each one of the relay. So in this case, this circuit breaker is a downstream circuit breaker that is near or your last load. And the circuit breaker here is the upstream circuit breaker that is connected to your incoming line. So this one here is the last one to trip, okay, when working your way up. So the tripping time that you calculate here must not be greater than the tripping time for this relay 1. So this relay 1 should have the higher tripping time. So that the protections is ensured from one section to another. Okay, now having said that, let's go ahead without any further ado to calculate the tripping time for relay 4. Now, before determining the plug settings, we knew already that if you watch that tutorial, that relay 4 is protecting the load on Busbar 5. So that we know. So this means this relay 4 is looking out for the fault or the short circuit current on Busbar 5, that is 2144 amp. Okay, now the first thing to do is to calculate the multiple of setting current. So for relay 4, that is looking out for fault on Busbar 5. The multiple of setting current M is then given by the formula M is equal to the fault current divided by the CT ratio times your nominal current of your CT plus times the plug settings. Now the nominal current is 1 amp. We have a plug setting, so we can then replace everything, and then we find M is equal to 4.9. The next thing is then to calculate TC. Now TC, if you watch my IDMT tutorial, we talk about the different standard for TC now. Now this TC is related to your characteristics curve for your IDMT relay. Now TC is equal to 3 over log M is your standard characteristics. You already calculate M, so you can then just replace in the formula, and you find that TC is equal to 4.35 seconds. So that is the operating time of that IDMT relay. We move on. The next thing to calculate is your TMS, that is your time multiplier setting, and that is given by the formula TA is divided by TC. But then we don't have TA. Okay, where do we get TA? The actual tripping time. How do we decide what is the actual tripping time for R4 for a fault on Busbar 5? Now there is a standard discrimination value that is equal to 0.4 seconds. TA is equal to 0.4 standard discriminations. Now this number here is based on 4 factors that determine the duration of operation. That is the actual tripping time. Now those 4 factors are also known as the grading margin. So number 1 is the variation from the ID characteristics, and that takes account of 0.1 second. Now the second one is the overshoot, and that's take account of about 0.5 seconds, and that is because of the disk rotation that continue to turn even when the relay call is no longer energized. So you have to take account of that 0.05 second. Now the third point is the circuit breaker operating time, because you have to remember that you have a relay that is sending a signal to your circuit breaker, and your circuit break only when your circuit breaker trip, then you have interruption into the current. So you have to take account of the operating time of your circuit breaker of 0.15 second. And the last point, that is your contact gap, 0.1 seconds must be allowed for your relay contact gap. So if you add up all of these factors, you're going to get 0.4. That's where the 0.4 standard discriminations is taken into account. So now continuing for our TMS calculation, we find a value of 0.092. Now moving on, we then go to relay 4 for a fault on busbar 4. So you have to follow how we calculating this thing. First, we do this relay is looking out for the fault on busbar 5. Now the same relay must look out for a fault on busbar 4. Now for a fault on busbar 4, we then need to calculate the multiple offsetting current again. But now this time we must use the current, the fault current on busbar 4. And we found the value of M to be equal to 5,166, and from that we can also calculate TC, and we found a TC that is equal to 4,21 second. And then we move on to calculate TA. Now remember, the first actual tripping time for this relay was based on the standard discrimination, but the second for busbar 4, we then need to calculate it using the TMS value. So using the TMS value, we can then deduce that TA is equal to TMS times TC. But TMS, the value of TMS, we have to use the TMS that we calculated for the fault on busbar 5. Because remember, this circuit breaker, okay, must discriminate between the two faults here, either on busbar 5 or on busbar 4. So to calculate the actual tripping time for busbar 4, we have to look at the time multiplier setting that we got when we calculated for the fault on busbar 5. So replacing the value, we get a TA that is equal to 0.387 seconds. Okay, so you can see that roughly the actual tripping time for the fault on busbar 4 is slightly less than the tripping time for a fault on busbar 5. That is based on the standard discriminations. Okay, we're going to stop here because this tutorial is going to get very long. So in the next tutorial, we're going to continue. That means we need to do for relay 3. That is for both busbar 3 and 4. Relay 2, relay 1, and so forth. So stay tuned for part 2 to conclude the design of this electrical network. Okay, so guys, if you like this tutorial, please don't forget to give it a thumbs up and subscribe to CMTEQ channel. Please hit the notification bell so that you don't miss the next tutorial. I thank you. Hey guys, welcome back to this tutorial on power system network design. This is tutorial number 7, part 7B. Now in the previous tutorial, which is part A, we calculated the tripping time for relay number 4. Now relay number 4 is looking out for the fault on busbar 5. As we can see, there is a current of 2.1 kiloamps. Now the same relay number 4 must also trip in case there is a fault on busbar 4, that is 2.2, slightly higher. Now because this is a downstream arrangement, so we're working from the bottom up. So the last relay in this arrangement must have the lowest tripping time than the first relay that is close to the power source. Okay, so now in this tutorial we're going to continue with relay number 3, because we've already calculated the time multiplier setting and we already calculated the actual tripping time for relay 4, either when there is a fault on busbar 5 or busbar 4. Now before I continue, I'd like to highlight the procedures in which to calculate this tripping time. As you have seen in the previous tutorial for relay 4, we first calculated M, which is the multiple of setting current. After calculating that, we then calculate the TC, okay, which is the operating time of the relay. Now after calculating that, we then calculate the TMS, which is the time multiplier settings. Now from that, we then go on and calculate the actual tripping time of the relay. So this is how you go about. So you cannot start by calculating TMS or TC, because you first need M before you calculate TC, and from TC you can get either TMS and also calculate TA. Now because relay 4 is the first relay to trip when there is a fault on busbar 5, so we assume that that relay must trip within 0.4 seconds. Now 0.4 second, we explained that it comes from the grading margins. Okay, now that is the standard discriminations, and then from that 0.4 we then calculated TMS of that relay for a fault on busbar 4, which we got the value of 0.092, and from there we could then calculate the TA for busbar 4, which we got a value of 0.387 seconds. Now continuing, we're now going to move on to relay number 3. Now for relay number 3, the first thing to do is then to calculate for a fault on busbar 4. So that is now this relay here, which got a plug setting of 200% and the CT is 201, compared to this one that's got a CT ratio of 250:1 and the plug setting of 175%. So now we move to relay 4, looking out for the fault on busbar 4, that is 2.2 kiloamp. So now as we've already illustrated here, the first thing to calculate is to calculate M. M is given by the following formula, that is I fault divided by the CT ratio times RN times your plug settings. Now we already know everything in our formulas. There is no unknown value, so we can just go ahead and replace. So we find an M that is equal to 5.651. That is the multiple of current settings. Now from there we can then calculate TC, which is the operating time. Now TC for the standard characteristics curve, we got TC that is 3 over log M, and we found the value of 4 seconds. The next thing to do is then to calculate TMS, the time multiplier setting. Now TMS is given by TA divided by TC. We already know TC, but we don't know TA. But we know that TA, for every relay, there is a 0.4% standard discrimination for the grading margin that is added to the relay. But because there was a previous TA that we calculated for a fault on busbar 4, that is now 0.387 second. So we need to add that 0.38 second to the 0.4 standard discrimination. So we then get a TA of 0.787. Now that is to ensure that if there is a fault on this busbar, this relay here, R3, must not trip before relay 4 trip. Because if relay 3 trip before relay 4, that is now defeating this relay 4. Because if this part of the circuit does not have a problem, there is a problem on this part, so R4 should trip. This is why we're adding that standard discrimination, that grading margin, to the TA of relay 4 on busbar 4 to ensure exactly that relay got a slightly higher tripping time. So then we find that TA, and then we can then calculate our TMS, that is TA over TC. So we found now a TMS of 0.197. Are you following me, guys? Please pay attention, because this is exactly the procedure you do to determine this tripping time. If you follow the procedure carefully, there is no room for error and you're not going to make mistakes. So you're going to get your full mark. Now we move on to the next one. So that is the same relay, but this time we want to look for the fault on busbar 3. Okay, before we go any further, please guys, hit the like button and the subscribe button. That's all I'm asking. Subscribe to CMTEQ channel so I can keep doing this tutorial. Then I know there are people out there who want more tutorial like this. Hit the subscribe button now and the like button. Thank you very much. Okay, so now moving forward, we then calculate M. So our M here will then be 1.6 kilo M divided by 200 times 1 times 2. And that is equal to 4.19. And then from there, we can then calculate TC. TC will give us a time of 4.82 seconds. So that is our operating time for that relay 3 for a fault on busbar 3. Okay. So the next thing then, since we already determined M, we need now to calculate for relay 3 on a fault on busbar 3. So that TMS is then equal to same formula, TA divided by TC. And then we can then go ahead, since we already know TMS of the previous fault. So you must follow the procedure, because where you're going to get this TMS, you get this TMS, the same TMS that you calculated when you were doing that same relay, but for a fault on busbar 4. That's a TMS you're going to use now to calculate the TA now for that same relay for a fault on busbar 3. So that gives us a time of 0.95 seconds. So that is now the answer for TA, the actual tripping time for relay 3 for a fault on busbar 3 will then be slightly under 1 second. So we've done now with relay 3 for the fault on either busbar 3 or busbar 4. So we now move into relay 2. So relay 2, we also need to calculate for a fault on busbar 3 first and then on busbar 2. So there we go, relay 2 for a fault on busbar 3. So we calculate M and then we get the value exactly the same, because we have the same plug setting and the same CT ratio. So nothing is going to change here. We got exactly the same TC of 4.82 seconds. Now we move on to calculate now TMS. So we have to also add a 0.4 standard discrimination. This is to prevent that this relay trip first before this relay. So we do that, and then we got a TA of 1.35 seconds. And from there we can calculate our TMS. TMS is then equal to 0.28. Okay, so that's a time multiplier settings for relay 2 on a fault for busbar 3. Now remember, we're going to use this TMS value to calculate the TA for the same relay, but this time when the fault is going to be on busbar 2. So moving on, we know that TMS for busbar 3 is equal to 0.28. Now we move to the next one. So that is now going to be for relay 2 for a fault on busbar 2, since we already calculated relay 2 for a fault on busbar 3. We then need to calculate for a fault on busbar 2. Please guys, pay attention to the procedure as illustrated here. We know that we need to calculate first M, TC, TMS, TA. but keeping in mind that every time you have to calculate TA, you have to use TMS of the previous one. So every time you have to calculate TMS, you have to use TA of the previous busbar fault, and you have to add TA of the grading margin so that you can get a higher actual tripping time. Okay, so now let's move on and calculate M for the relay 2 for a fault on busbar 2. So we know that busbar 2, the fault is that 1.7 kiloamps. So we replace the value and then we find 4.36. And then we can then deduce our TC for the standard characteristics curve. That is equal to then 4.69 seconds. Basically 4.7 seconds. Okay. Now from here, we then go ahead and calculate TMS as we have discussed. So TMS is TA over TC. Remember these formulas because they don't give you the formula sheet, but you have to remember the procedures. But then remember here, TMS. So you already have TC, but where do you get TMS? TMS is the previous TMS that you calculated for relay 2 when you were dealing with the fault on busbar 3. And we saw that on the previous slide, we saw that that value we calculated was 0.28. Okay, so you have to then multiply that TMS value times your TC to get now your new TA for this relay. And you can clearly see that this TA is equal to 1.31 seconds. So TA for relay 2 for a fault on busbar 2 is equal to 1.31 seconds. Please pay attention, guys. Okay, so now we've done with relay 2 for both the fault on busbar 2 and busbar 3. So now we move on to relay 1. Now, just like we've done for relay 2, we've calculated for the fault on either one of the busbar. Now we have to do the same for relay 1 for the fault on busbar 2 and for the fault on busbar 1. So we first start for the fault on busbar 2 as we've done previously. So relay 1 for the fault on busbar 2. Procedures. So we must first calculate M. Our M is given by the same formula. We replace the values. We can see that the fault on busbar 2 is 1.7 kiloamps. Okay. And then we get a value of 4.36. It's exactly the same value there. From there, we can then calculate TC since we already found the value of M. And then we can then replace. So our TC here will be equal to 4.69 seconds. Okay. It's exactly the same TC as there because this relay and this relay, they have exactly the same Plugsettings. So we are calculating from the same fault on busbar 2. Okay, so you get exactly the same thing. Now the next thing then here is to calculate TMS. Okay, so TMS, as we know, is TA over TC. But remember to add the 0.4 standard discrimination. Okay, then that gives a value of TA that is equal to 0.4 plus 1.31 seconds. 1.31 second, that is this one that we calculated for relay 2 for the fault on busbar 2. This one. Because remember, we are also now calculating the TMS for relay 1 for the fault on busbar 2. So we have to use the TA that we calculated when we were calculating for relay 2 for the fault on busbar 2. That's the procedure, guys. So you just following section by section. This is how protections is provided when you use IDMT relay with grading margins in a differential protection setup. Okay, so now we can go ahead and calculate our TMS. That is now equal to 0.375. Now remember this TMS, you're going to use this TMS to calculate the TA for the same relay, but this time when you calculate for the fault on busbar 1. Okay, so we move on. Relay 1 for the fault on busbar 1. We calculate M. Notice that's now the fault on busbar 1. That is the 1.8 kiloamps. So we get 4.55 for M. And then we calculate TC, that is 4.56. And then with our TC, we can then go ahead and calculate TA, because TMS is TA over TC, so TA is equal to TMS times TC. So we have TC, we should also have TMS, that is 0.375 there. So we can just replace, so we find a TA of 1.71 seconds. So you can clearly see there is a grading margin difference here. We then find a TA on busbar 1 for relay 1 of 1.71 seconds. Now, as you can see, from the very first relay 4, with the fault on busbar 4, there was a 0.4 second for the grading margin. We have now the last relay here is going to trip for a fault on busbar 1 on a time of 1.71 seconds. Now, why are these times not the same? Because let's say there is a fault on this busbar, and if this relay here fail to trip within 0.4 seconds, this one is going to trip. If this one fail to trip, this one is going to trip. If this one fail to trip, it's R2, and within 1.7 seconds, R1 is going to trip and cut off the whole power. Because if there is a short circuit here, there will be a higher current that is going to start flowing. So all of these relays are going to see that something is not right, so the power is going to trip. So that is how protection is ensured in this 5 busbar downstream arrangement. Okay, and for most national electrical standard and regulations, this tripping time must be less than 2 seconds. So it cannot be over 2 seconds. That is too much of a time. A lot of things can already start burning. So it happened very fast. But if there is a fault somewhere along busbar 1, and it happened instantaneously, and it tripped the circuit. So that is how this busbar arrangement is done. So guys, don't forget to subscribe to CMTEQ channel and give the thumbs up to this tutorial. And please stay tuned and come back for more tutorial like this. I thank you. Cheers.